Welcome back to Monday Bagel, your go-to podcast exploring the fascinating intersection of AI, law, and technology. I'm your host, Michał Jackowski, and today we are diving into a truly cutting-edge topic, quantum computing in 2025 and its implications for the legal world as well. Joining me is someone who needs no introduction in the tech world, Dr. Jan Rainer Lahmann. Jan is an IBM Distinguished Engineer and was named #1 LinkedIn Quantum Top Voice of 2024. He works over 2 decades at IBM and he's led projects ranging from the first petaflop supercomputer in Germany to driving the enterprise adoption and application of quantum computing technologies. Jan, thank you for joining us today.
Yeah, thanks for inviting me for this podcast.
Let's start from the big picture. How would you describe the current state of quantum computing at the start of 2025? Have we reached any significant milestones in terms of computational power or real-world applications?
Yeah, so the big milestone that everybody is looking forward to is what we call quantum advantage. That is when quantum computers can solve some practically relevant problems faster, better, or cheaper than traditional computers alone. And I said we are looking forward to that. So very clearly, quantum advantage has not yet been achieved in the industry. Yeah. So as of today, traditional computers are, in that sense, better than quantum computers. Because of that, quantum computers are not yet in production. Yeah, so there are no production applications running on quantum computers. But the important milestone that we have achieved, actually mid of 23, is what we call quantum utility. And that means that in some sense, quantum computers for a very specific application, I can mention that in a second, for that specific application, quantum computers are as good as the best exact classical methods on classical computers. And that research paper that was looking at a very specific problem from physics, it's called an Ising model, that is about magnetization of materials. So clearly that is not the industry application that everybody is looking forward to, but a very important milestone that we are now, at least for the first applications, on the same level as classical compute. And of course, we are working on broadening that to other applications. There have been quite a number of additional publications with the same quality of result, and also bringing that to really practically relevant industry applications. The areas that people are typically looking at in quantum computing is simulation of quantum mechanical systems. And that includes material research, quantum chemistry, and these things. And that was also the original idea where the idea of quantum computing first came up. Second area is machine learning and artificial intelligence. And the third area is optimization, like routing optimization, supply chain optimization. And these are the three big areas where people are looking at. We already have developed algorithms. We have implemented, or people have implemented first applications, but typically on a smaller scale. So not really on that quantum advantage scale.
So if there is the same level of power or capabilities, why is there so much hype in quantum?
Yes. So definitely the status that we have now, that is not the final goal. Yeah, we are really expecting this and working towards that quantum advantage. And the leader in IBM for quantum computing, Jay Gambetta, in December, he said that his expectation is, his prediction is that quantum advantage will be achieved and can be achieved within 2 years. So that is by the end of 2026. And advantage can really be disruptive. Yeah. To give one example, but this is not the key application that we see for quantum computing, but that is related to encryption, to security. And the mathematical core of that is factoring numbers. And for large numbers, the prime factorization on traditional computers takes a couple of billion of CPU years. And a quantum computer, once they are a bit larger and have a bit higher quality, they will be able to do that in a couple of hours. Yeah. And so that is the potential improvement that people are expecting. For other use cases, it might be not that extreme, from billions of years to a couple of hours. But still, if you have only a few orders of magnitude or one order of magnitude improvement, that is a huge step, and can provide enormous benefits.
Okay, you mentioned some use cases that can adopt quantum computing, but what businesses and research institutions are currently assessing quantum computing capabilities, and which of them can use them in future? Which industries are currently best positioned to take advantage of quantum computing?
So many industries are looking at quantum computing, and disruptive potential, as we described or as we discussed, is really big. The first area, simulating quantum mechanics, that probably is not relevant for all of the industries, So material science, quantum chemistry, these are only specific industries. For example, automotive, basically all of the large automotive manufacturers, they are looking at developing new materials for batteries, for electromobility. So there are first implementations on quantum computers, but for smaller problems, for smaller like molecules, then you would need for really new batteries. Also in the finance industry, investment banking, they are looking at quantum computing. And if you have some improvements in like portfolio optimization and risk assessments, there's a huge leverage and a huge potential financial benefit with that, but also other industries, manufacturing. So it goes through all of the industries. And the use case areas that I mentioned, like machine learning, artificial intelligence, and optimization, you can find use cases in all of the industries.
Can you elaborate a bit how they can leverage quantum computing, maybe in connection with artificial intelligence?
Yes.
It's extremely interesting.
Yes. So there are several ways to combine quantum computing and artificial intelligence. What many people from quantum computing first think of is running machine learning algorithms on a quantum computer. So that is one option. And there are already machine learning, artificial intelligence algorithms, but they are a bit different than you would first think. So maybe a bit surprising statement, quantum computers are not big data machines. Quantum computers are small data, big compute. And at first glance, that does not seem to fit with artificial intelligence, because you think it's always a huge amounts of data. But there are certain parts of AI algorithms that need more compute and less data. And for these specific parts of algorithms, there you will be able to use quantum computers. And that already indicates that we think that quantum computers will not replace traditional computers, but it will typically be a hybrid scenario. So the algorithms and also the infrastructure will be a combination of quantum computers and traditional computers. One way to see it is today we have CPUs, so the classical CPUs, and we have GPUs, the graphic units, where you can run specific parts of algorithms, also AI algorithms. And in the future, we will have an additional option in the compute infrastructure that is a QPU, a quantum processing unit. And then the operating system or the algorithm has to decide which parts of the compute to run on which element of that compute infrastructure.
Okay, really interesting. Quantum computer is quite expensive. I know that the research or businesses or research institutions use it via remote connections rather than building the computers themselves. Is that so? How does it look like? And can you elaborate a bit on that?
Yes. So the investment that we and others have made into developing quantum computers and the algorithms, they are enormous. And the idea was first discussed in 1981, so more than 40 years ago. And so it's been a long period of investments in research and development and building the first systems. I don't have concrete numbers, but that is into the billions of dollars, obviously. And as you correctly say, typically quantum computers are used over the cloud. So they are located in quantum data centers and are being accessed over the cloud. There are specific software frameworks to program quantum computers. The very widely used one is called Qiskit that supports the IBM quantum computing hardware, but also other vendors. And that is based on Python. Yeah, so that is a well-known programming language. So that is not the big hurdle, but the logic to really develop the algorithms, that is completely different for quantum computers compared to traditional compute. Yeah, so for the access, typically cloud-based, it is also possible to install a system on-premise. Yeah, we have around 5 or 6 systems installed worldwide at client premises. Again, a bit surprising maybe, the simplest way to access real quantum computers is actually for free. From IBM, we have something called an open plan. And so everybody is entitled to use a real quantum computer per month for 10 minutes. Yeah, so it's not unlimited, but 10 minutes of quantum QPU time is free of charge. Yeah, and then of course there are also paid plans for more extensive access.
Okay, I will try and use it maybe this month. But here comes the law. And from the legal perspective, what challenges arise when providing quantum computing as a service? I can see level of service as a novel service. I can see data security. You mentioned already encryption and all these things related to data security. I can see cross-border data flows as a matter to regulate and to solve. Maybe also liability for this level of services. So, are you involved in such the ideas, and how do you solve these problems?
Yeah, so I would not claim that we have solved it, but of course that's a very important aspect. Yeah, so for any new and groundbreaking technology, that is definitely something that needs to be looked at and carefully thought through. And that also applies to quantum computing. So in IBM, we have a team that deals with, we call it responsible quantum computing. Yeah, so, and that means quantum computing and really being conscious of the effects of the implications of that new technology. From the risk, everything that you said is valid, but currently I think the main direction for quantum computing is doing things that we can already do better. Yeah, and in that sense, I do not see any really completely new risk. Yeah, except for breaking encryption. Yeah, so that is what we already mentioned. That definitely is a risk to IT security, to data confidentiality. Yeah, so we can discuss that maybe a bit later in more detail. But definitely that is the key risk. And I think we need to carefully look at that. And over time, people will have completely new and novel ideas how to use quantum computers in ways that we cannot imagine today. Yeah, for example, I mean with the internet. Yeah, technically speaking, you can transfer some bits, some data. Yeah, but the possibilities that then arose and did arise, and the ideas that people had how to use the internet, that goes way beyond. Yeah. And that we have to monitor and to anticipate and then see when these ideas emerge, what that means and what kinds of policies that maybe would require.
So, terms of use of such the QC as a service is not really different from let's say general tech terms of use, terms of services. I can imagine because of novelty of such the technology, it may be not as stable, so you cannot guarantee as much as normal traditional technology and be liable as a normal technological company providing, let's say, traditional services.
That is correct. So, as we said earlier, quantum computers are not yet in production. Yeah, so we do not offer the same service level agreements like uptime and redundancy as for other technology. But you can access the IBM quantum computers on the IBM Cloud. And the main contract that is needed for that is the standard cloud service agreement. Yeah. Okay. And then there are just a few additional provisions. It's like a 4-page additional contract that needs to be signed to access the quantum computers, the quantum systems. And the additional terms is we have some restricted countries. Yeah, so these systems are not available they are available in most countries of the world, but not in all of the countries. Yeah, and I mean, everybody can imagine what's excluded there. And then the contract also says that the systems may not be used for breaking encryption and not be used for any development or testing of weapons of any kind. Yeah.
Okay.
So these are the specific terms, but the rest is standard cloud agreement.
Okay, not very different. And quantum systems process vast amounts of data. And how do you see issues like data sovereignty or jurisdiction affecting the adoption of quantum computing, especially when you mentioned that quite highly regulated industries like pharmaceuticals or chemistry or finance are looking at this technology? How to handle with it?
I think a key aspect is locality. Yeah. Both of the hardware and of the data. And I mean, we know this discussion for any part of the world, including the EU, that is important to have that local. Yeah. That is something that is developing, that is emerging. We have opened our second quantum data center worldwide in the EU, in Germany in that case. With the appropriate configuration, there's also data locality. Yeah, that means that all of the relevant data, so the data that you input, that you get out of it, and also the programs, we call that quantum circuits, that stays physically in the EU. Yeah. And so, I mean, that is the example for IBM. Other vendors will follow that approach, yeah, and will also have similar services. Yes, I think that hardware and data locality, that is the key aspect there.
Yeah, that's interesting. So you can guarantee that data is stored within EU when EU businesses want to be compliant with GDPR, for instance.
Yes. So as you mentioned, GDPR, that's interesting because GDPR does not require the hardware or the data to be in any specific part of the world or country. GDPR compliant processing can be done anywhere in the world, and all of again, the example of IBM, all of the services that we offer are GDPR compliant, even if they are implemented in the US or somewhere else. But in this case, yes, you can configure the quantum computing service in a way that all of the relevant data really stays in the EU. Yes.
Okay. Really interesting. And one more questions I'm curious about is whether regulators are approaching you and discussing, or at least looking at this new technology. Because the question if they are really aware of this development of technology.
Yeah. Yes. So there's a huge interest in this technology because I mean, quantum computing is the only compute technology that has this potential, this disruptive potential. And frankly, AI has a higher focus currently. Yeah. So, and because it's also on the timeline a bit earlier than quantum computing. Yeah. Quantum computing still is a bit in the future. There are standardization initiatives and also conversations with legislators and so on. And I think that is very important. Yeah.
You mentioned that quantum computers have really big potential to break current encryption standards, and it's a topic that it's discussed. So how soon do you think organizations need to transition to quantum safe cryptography, and what legal obligations might arise during this shift?
Yes. So maybe first a short description of the challenge, of the risk, yeah, and then you already mentioned quantum safe encryption. So as we mentioned, quantum computers at some point in the future, it is not clear when that will happen. So that will definitely be not in 2 years. That requires much more powerful and larger quantum computers. So it will be a couple of years out. Yeah, it is not yet clear when that will happen. But then quantum computers will be able to break what is called the asymmetric encryption. Yeah, that is based on factoring numbers. Okay, so and that is a risk not only for data confidentiality, but also for signatures, for example. So I sometimes say, if someone can read my bank account data, in 20 years from now or in 15 years from now, I don't care. Also my health data, but every organization, every enterprise has data where they definitely want to avoid that people can decrypt the data that they have encrypted today. And a key aspect is that this attack has already started, because attackers are already saving encrypted data, that they get hold of on the internet or at other places, and then they just wait, for how many years? So 5 years, 10 years, 15 years, and then it is pretty clear, and everybody agrees that then it will be possible to decrypt that data. And so this is really an urgent topic. So every organization must act now and analyze their data, identify what is really the critical data where they need to avoid this decryption in 15 years from now. And the good message is, as you already said, there are quantum safe encryption methods. And these quantum safe algorithms, they can run on traditional hardware. So you do not need a quantum computer to protect against this potential future quantum computing attack. And now, so from a scientific perspective, the problem is solved. I mean, the quantum safe algorithms, they exist, they have been standardized, but it is a significant operational problem, really to identify where in my whole IT infrastructure do I have encryption algorithms, libraries used, and then update them to a quantum safe version. And it is pretty clear that this will take years to do this switch to these already existing quantum safe algorithms.
So do I understand it properly that even the data leak of encrypted data today is a danger for organizations if they don't use these safe techniques?
Absolutely, So that is the key risk, Yes, as you say.
Okay.
The attacker stores this encrypted data and waits for 5 years, 10 years, 15 years, and then they decrypt the data, and then you cannot re-encrypt it with better algorithms later. That's impossible. You have to act now.
Okay, so it's a good message, good call to action. Be prepared for quantum computing in the future. Beyond security, what ethical concerns do you foresee with quantum computing? Some kind of misuse, surveillance, military applications, some other aspects?
Yes. So I think the risk for encryption, that is the major risk. And then I mentioned this responsible quantum computing initiative and team that we have. And so they have defined some principles for IBM quantum computing, and I could mention them. So one of the principles is that we want to make a positive societal impact with quantum computing. Mm-hmm. It sounds a bit abstract, but I think it is important to have this aspiration and these principles. Then exploring the use cases with some foresight, because as we discussed, completely new ideas will emerge how to use quantum computers and what to do with them. Unfortunately, I don't have a good example here because this is something that will happen in the future. Mm-hmm. Okay, then also important to be accurate about the description of the capabilities and the expectations. So we are really conscious about not creating and overhyping that technology. But as we started, I mean, I clearly said quantum advantage has not been achieved yet. And so that is that's part of being neutral and have a neutral description of that technology. Okay, and then also the community, the ecosystem is very important for us, and to building a diverse and inclusive quantum community. That is one of the other principles that we have there.
Do you know any global efforts to standardize and regulate quantum computing? Because you mentioned your internal guidelines, but there are no laws so far regarding quantum computing itself. But are there any initiatives? I heard about ISO works on standardization of quantum computing, but how far it is?
So there are several standardization initiatives also on various levels of the quantum computing stack. Yeah. So one example is it's called OpenQASM that defines the interfaces and how algorithms are being mapped to the quantum computing hardware and then executed there. There are also, I would call it de facto standards, yeah, like Qiskit, and that is the most used quantum software framework, which supports many different kinds of quantum computing hardware. I would say there is not a single standard. Yeah, there are multiple activities and initiatives, and clearly this an international collaboration would be or is very important. Yeah, so that we do not have different standards in different parts of the world. So for me, this collaboration, yeah, is very important for standardization, but also in terms of the technology. Yeah, I mean. In today's world, to me, it seems to be impossible if you would say, okay, we want to develop the whole technology stack for example, in the EU only. Yeah, because it's such a huge effort for the hardware, the software environment, applications, then the use case research that needs to be done. And if we would try to do that in Europe alone, yeah, we would be years behind in reaching a quantum advantage. Yeah, so that needs to be a good balance, yeah, between collaboration and also sovereignty, of course.
So maybe one last question about the legal technology itself. Do you foresee quantum computing playing a role in legal technology itself? Could it transform areas such as legal research, analysis, contract analysis? Because we are speaking for 2 years about how AI transforms law. It has some impact, maybe not as high as it seemed like 2 years ago, but can quantum computing do it, or in combination with AI? What's your idea?
So I must admit, I do not have a concrete use case for that. But I mean, as we discussed, I think that quantum computing is or has use cases in basically any industry. Yeah, and that includes legal. Yeah, and so for all industries now, or the current state of the technology is that it is key to identify the use cases, yeah, where quantum computing could help. And I mean, primarily quantum computing can help if there is a limitation with compute capacity. And I'm not aware where that is the case in the legal environment. Probably in legal, you do not need supercomputers and also the original idea of quantum computing with simulating quantum mechanical systems. Yeah, that is not applicable. But what I could imagine is actually in machine learning and AI. Yeah. The expectation is that with quantum computers, you can build better machine learning models, so with higher accuracy, using less training data. Yeah, and that could be something that can be interesting and has applications also in the legal environment.
Can it lead to cheaper technology? Because we all now hear that costs of learning of the models are really expensive.
Yeah. Yeah, I mean, that's a big topic, the compute effort and also the energy consumption for training large language models. Yeah, I mean, that is huge. So unfortunately, that specific problem cannot be directly addressed with quantum computers. So there is no algorithm known where you can train the large language models as they are today, yeah, with a quantum computer. Probably it would need different approaches. There is a research already for a different form of natural language processing that better fits to quantum computers and to the world of quantum mechanics. Yeah. So it's a bit further out, but yeah, so there are some ideas how to address that.
So to summarize, we have 2 years more until the quantum computing technology reaches the advantage in our world. We should be prepared for it now because of these encryption threats, and
Yeah.
we should also think about use cases, especially in the legal world, when we can use new computational power. Is that so?
Yes, and I mean, for me, these two topics, useful applications of quantum computing and quantum safe encryption, these are separate topics. Yeah. Uh, and for the useful applications, yes, we expect quantum advantage to be achieved within the next 2 years. That does not mean that we then have an advantage for any use cases and for any algorithm. Yeah. So it starts with probably with a specific area with specific use cases, and then will be broadened, yeah, to other use cases, to other industries. Okay, so that is 2 years out. Other use cases maybe even a bit more, but the time to prepare for that is not too long. Yeah, I mean, it's a very different technology, very different implementations, completely new algorithms, and really understanding the capabilities of the technology and the potential benefits. That is something that that organizations should start to look at, yeah, if they have not done it yet. And for quantum safe, that is really urgent, yeah, as we discussed, to really identify what is my critical data, yeah, what encryption schemes do I use today, and where and how do I switch to quantum safe encryption? Yeah.
And I think the important information that you can use it for free for 10 minutes a month using IBM Cloud. So all the people that listen to this podcast can do it even now. Thank you, Jan, for this fascinating conversation, for sharing your insights into the world of quantum computing and potential impact on the legal field. Thank you.
Yeah, thanks a lot for the invite, Michael. And yeah, maybe we can speak again end of 26 and see for what use case we have achieved a quantum advantage by then.
I hope so. And for our listeners, don't forget to check out more about Jan and his work at IBM Quantum. And if you enjoyed this episode, make sure to subscribe to Monday Bagel, leave a comment, share the episode with anyone interested in the future of technology and law. Bye bye.